Thanks again. I'll get us started with some setup. So I'm going to let H be a complex Hilbert space. A is going to be a C-star subalgebra of B of H, otherwise known as a concrete C-star algebra. And for those of you who don't know, this is a star subalgebra of B of H, the bounded operators on H, that is closed in the norm topology, the operator norm topology. And as is common, I will write A sub SA for self-adjoint for the self-adjoint elements of A. And now I'll build some notation for continuous functional calculus. So if you have a scalar function from the real line to the complex numbers, I'm going to write F tilde for the map that takes a self-adjoint element of A and maps it to the operator F of A. And for those of you who don't know, roughly speaking, this functional calculus is first defined for F, a polynomial, in the only way that makes any sense, the appropriate polynomial of A. And then it is extended to continuous functions F via approximation. So that's known as functional calculus. And again, I will refer to the map A maps to F of A as F tilde. Now, my co-advisors at UCSD are Bruce Driver and Todd Kemp, and they had the same advisor, Leonard Gross. And he told them, and they told me, that if you have a function, you should differentiate it. So the goal today is going to be to discuss the smoothness properties of this operator function, F tilde, in terms of the smoothness properties of the scalar function F. This turns out to be a pretty difficult problem. And I'm going to sidestep the actual definition of what I mean by smoothness. For those in the know, anything I say will be in terms of Frechet smoothness or Frechet derivatives of maps between norm vector spaces. But I will write everything in terms of directional derivatives because it's easier to write down and understand. All right. So before getting to some motivation, I'll give you a little bit of history. So problems of this nature have been studied quite extensively, and they were the reason that these so-called multiple operator integrals were invented. And the seminal work took place in 1956 with this paper of Daletsky and Crane, which studied the case of A is n by n matrices, and then also more generally, A is all of bounded operators on the Hilbert space. And then there was later a connection noticed with some earlier work of Loevner that I'll talk about in a little bit. And that led to an explosion of work by Bierman and Solomiak, and then later Peller in the case of one derivative. Then there was also some breakthroughs by Stenkin and Peller, most importantly, this 2006 paper in the case of higher derivatives. This 2010 paper right here is a bigger paper on matrix analysis, but the reason I included it is it's a useful current reference that discusses some of this Daletsky-Crane material in more modern language. So that's why I put that there. And then finally, there's been plenty of work also in the case of A being a semi-finite von Neumann algebra due to de Pacter, Sukochev, and Asamov, Carey, Dodds, and Sukochev. Couple of remarks. So many of the above references consider differentiating the operator function at an unbounded operator, or if you know what this means, in the case of a semi-finite von Neumann algebra, an affiliated operator. And this is one reason that C-star algebras are not really considered. Second, this list I just gave you is very abbreviated. Multiple operator integrals have lots of really cool applications, and there are lots of different approaches to them. And this list is very not complete, even in terms of the applications to differentiating operator functions. But what I would highly recommend you to do if you want to learn more is look at this Skripka-Tomskova book, Multilinear Operator Integrals. It's a nice comprehensive survey of what's known so far. All right, with that history behind us, I will give some motivation in the finite dimensional case of matrices. And for that, I'll do some preliminary setup of some notation. So if A is a Hermitian matrix, i.e. an n by n matrix whose conjugate transposes itself, then by the linear algebra spectral theorem, A is unitarily diagonalizable. Now, in my opinion, the best way to say that is in terms of the spectral resolution of A. So equivalently, A can be expressed as this sum over the eigenvalues lambda of lambda times p lambda A, where p lambda A is the standard matrix representation of the orthogonal projection onto the lambda eigenspace of A. And as I just said, this is called the spectral resolution of A. And the p lambdas they are a resolution of the identity, i.e. they satisfy that number one, they sum up to the identity, and that just means that the eigenspaces span all of C to the n, the whole space. And then these two conditions together mean that P lambda A is an orthogonal projection, and that the ranges, i.e. the eigenspaces, are orthogonal. There a question? Okay. All right. So this spectral resolution view gives a nice way that's compatible with the infinite dimensional case of how to express functions of matrices. So if you have a function from the real line to the complex numbers, f, and we have our matrix A, f of A, or f tilde in the notation above, is expressed nicely as the sum over the eigenvalues lambda of A of f lambda P lambda A. All right, so I will use this view of unitary diagonalization, if you will. All right, now I'm going to spend some time deriving the derivative formula in the finite dimensional case that we will focus on later in the infinite dimensional case. So here is the formula. I claim that if A and B are Hermitian matrices and f is a C1 function, then this directional derivative of f tilde at the point A in the direction B, which is defined as usual to be this derivative at 0 of this curve, is given by the following expression. So double sum over the eigenvalues, lambda mu, of f of lambda minus f of mu over lambda minus mu. And if lambda is equal to mu, this is defined to be the derivative of f at lambda. This is, if f is C1, this is a continuous function of two variables. And then we do P lambda A, B, that's the direction, and P mu A. And I'll talk a little bit more about how to interpret such an expression in a little bit, but let's see how it arises first. So the way this is going to arise is as a limit of a perturbation formula, and I'll show you what that means. So first, we'll take B and A, and we will express f of B and f of A in terms of the spectral resolutions of B and A as in the previous slide. So f of B is this guy, and f of A is this guy. All right, so I only know a few tricks. I know how to add 0, and I know how to multiply by 1, at least. In this case, we're going to multiply by 1 in the form of the identity matrix as the sum over the eigenvalues, in this case, of P mu A. Remember, this the P mu A's sum up to 1. And then on this side, I'll do it on the left, and I'll do the sum of the P lambda B's. Now we have a sum over the same index set with the same indices. So we'll combine terms. We get this double sum over eigenvalues of B and A of f lambda minus f mu, P lambda B, P mu A. Now, once more, I'm going to multiply by 1 in the form of lambda minus mu over lambda minus mu. This gives us that function we were looking for, this difference quotient. And then we're left with lambda minus mu, P lambda B, P mu A. Now, I claim that this equals P lambda B times B minus A, P mu A. This may or may not be obvious to you, depending on how familiar with you are with the stuff, but I'll give a little calculation that shows it. All right, so if we look at the what I claim it is, we will express B and A in terms of their spectral resolutions. So there's B and there's A. Now I'll bring the PBs in and the PAs in. And in the B sum, we get all the terms that are not equal to lambda disappearing. And in the A sum, we'll get all the terms not equal to mu disappearing. So in the end, we're left with lambda P lambda B, P mu A minus mu P lambda B, P mu A, and that is what I claimed. All right, so if we take all of that together, we have expressed f of B minus f of A as this operation, where we do this two variable function, which I will call f bracket 1. This is known as the first divided difference of f, and we'll see higher divided differences later. I might say verbally f1 just for short. And the reason this is called a perturbation formula is if you view B as a perturbation of A by B minus A, what this says is that the nonlinear quantity f of B minus f of A is expressed as a linear operation that depends on B, A, and F applied to the perturbation B minus A. So this is the thing that Loebner proved in 1934. And now we're going to see how, well, first we're going to interpret this expression a little bit more, but then we're going to see how this perturbation formula leads to the derivative formula that I claimed. All right, so as I just said, this gives f of b minus f of a as a linear operation applied to the perturbation. And I built some notation for this linear operation. If you have a function of two variables phi, then I will define I be a of phi applied to a matrix C as the same double sum over the eigenvalues lambda of b and mu of a of phi of lambda mu, p lambda b, c, p mu a. So if we analyze this expression a little bit, and if we remember the expression for functional calculus in one variable, what this kind of looks like is we're taking this function of two variables, we're acting the first variable on the left of the input, and then we're acting the second variable on the right of the input. So this interpretation will be important later, but I thought I would point it out now that I've introduced this operation. All right, so now to prove the derivative formula, by definition, this directional derivative is this limit. And now if you plug in a plus tb for b up here, b minus a becomes tb, so the t's cancel. And I'm left with a plus tb, comma a, f1 of b. And now in the matrix case, it's not too hard to see, but I'll maybe leave it as an exercise, that it's a consequence of the continuity of f bracket 1, that this operation is continuous in these two inputs. And so I'm left with the formula that I claimed. So the I super AA of F1 applied to B. So that's this formula. Now I use the letter I to be suggestive for integral, and I'll explain why shortly. But first I will summarize what we've just seen and then tell you also the formula that you get if you repeat this for higher directional derivatives. Are there any questions before that? Cool. One more thing that I'll mention is that what I've just sketched to you is more or less the finite dimensional version of the standard proof of such results in the infinite dimensional case. And this proof technique can be adapted to unbounded operators, and that's one reason it's quite versatile and nice and people like it. I will actually opt for a different strategy, as I'll explain later. I will do an approximation by polynomials, which is actually closer to the original approach to such problems. But I'll mention more about that later. All right, to summarize what we just kind of sketched or derived, if f is a C1 scalar function, then f tilde is a C1 function from Hermitian matrices to matrices with derivative formula given by this. And now I'll give you the higher order version of this. And for that, we'll need a higher divided difference. So for f in CK, I'm going to define the kth divided difference, fk, as a function of k plus 1 variables defined inductively roughly as the first divided difference of the k minus first divided difference. And you actually do the first divided difference in this last variable, freezing all the rest of the variables. So we do this difference quotient of fk minus 1. I'll leave that formula right there to be digested for a little bit, and then I'll show you the derivative formula. Okay. So then the conclusion is that if f is ck, f tilde is ck from matrices to matrices, and the formula for the derivative, the kth directional derivative in the directions b1 through bk, is first a symmetrization in the input directions. This is a standard feature of Frechet derivatives. They're always symmetric in the directions, so you can more or less ignore this. Sk is the symmetric group on k letters, by the way. The important thing is this inside expression. So kind of similar to the above, we're going to have a k plus 1 fold sum over k plus 1 tuples of eigenvalues of A. And I will always write bold letters for k plus 1 tuples. Sometimes there'll be k plus 1 tuples of scalars. Sometimes there'll be k plus 1 tuples of operators. But that's my convention here. And what we're doing is we're taking this function, fk, of k plus 1 variables, acting the first variable all the way on the left, putting in the first input, dot, 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 kth variable, then the kth input, and finally I'll act the k plus first variable all the way on the right side. So that is the kth order formula in the matrix case that we will go after in the infinite dimensional case. Are there any questions so far? Great. All right, let's talk a little bit about maybe how to interpret these formulas to guess what they should be in the infinite dimensional case. So in the infinite dimensional case, the analog of the spectral theorem is that for a bounded self-adjoint operator, there is a unique projection valued spectral measure called PA. And I'll talk more about projection valued measures later, but for now, you can just view this as a generalization of that sum from before, that is the spectral resolution of A. So A is going to equal the integral over the spectrum of the scalar function lambda integrated with respect to the projection valued spectral measure of A, PA. All right, so if we look back at this formula, we've got this double sum over the spectrum and the P lambda A's and the P mu A's. So if we naively sort of replace those sums with integrals, we get the following guess, that if we're going to differentiate in the infinite dimensional case, the formula should maybe look something like this double integral. We have the same divided difference function integrated first in the first variable, slide the input in, and then integrate in the last variable. But then immediately, it's not quite clear how to make sense of this expression. If you're familiar with projection valued measures, the standard theory only lets you integrate scalar functions with respect to a projection valued measure. So actually, this inner integral is fine. It's a continuous scalar function of lambda integrated against PA, no problem. You can multiply by B, no problem. But this outer integral is an issue. This is an operator valued function of mu, and it's unclear how to integrate that against PA. And then there's a perhaps more serious problem that was shown by Farforovskaya in 1975 and Peller in 1985 and some more later, that in fact there is a separable Hilbert space H and a C1 function, so that that operator function F tilde is not CK. So maybe it looks, even though it looks like this should make sense all the time, there's kind of some hints that it shouldn't be able to make sense. And actually, morally speaking, and sometimes technically speaking, in the area of differentiating operator functions, more or less the entire difficulty of differentiating the operator function is in making sense of expressions like this. Slightly more precisely, the mantra in this field is that if you can make sense of the double operator integral, so that's this IAB phi at C, which is this formal double operator integral against two projection valued measures, for enough functions of two variables, then you can prove theorems that say your operator function is differentiable with derivative formula as you expected. More generally, for the kth order, if you can make sense of the multiple operator integral expression, and once again, let's study this expression a little bit. Phi is supposed to be a function of k plus 1 variables, and we do first the first variable, then one of the inputs, dot, dot, dot. Then the kth variable, then the kth input, and finally we act the k plus first variable all the way on the right. So that's this multiple operator integral notation. Turns out that if you can make sense of multiple operator integrals, then you can prove theorems that say your operator function is k times differentiable with kth directional derivative given by the symmetrization of the multiple operator integral of the kth divided difference of f with the k plus 1 tuple of all a's. So we take a1 dot 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 ak plus 1 all equal to a, and then applied to the symmetrized inputs. So I have now shifted the goal to making sense of these multiple operator integral expressions. And that is going to be the next topic of discussion. Before I get there, are there any questions or comments? Fantastic. All right, let's talk about multiple operator integrals. So before I do that, I'm going to give a quick review or rundown of projection valued measures. If you're familiar, this will be a review. If you're not, I'm sorry for going a bit fast, but here we go. So here's the definition. If you have a measurable space omega f and a complex Hilbert space H, a map P from F to B of H is called a projection valued measure if P of the whole space is the identity on H. P takes values in the orthogonal projections, i.e. P of G is self-adjoint and a projection for all G measurable sets. And finally, this function is countably additive in the weak operator topology. So that's the definition of a projection valued measure. And as a little remark, it's very common to include this requirement in the definition that P of an intersection is the product. That's actually redundant. It follows from these three. It's often included because if you assume this, then this series always exists in the weak operator topology. But if you just assume in the definition that it exists so that you can define countable additivity, this follows. Anyway, that's a side comment. So now a little fact we'll need is that if you take two elements of the Hilbert space, H and K, then the map that takes a measurable set G to what I'll call P sub HK of G, and I'll just define that as the inner product of PG applied to H, inner product with K. This map is a complex measure with total variation norm at most the product of the two of the norms of the two input vectors. So that's a little basic fact about projection valued measures, and it is what allows us to integrate against projection valued measures. So I'll go over the definition of projection valued integrals. So I'll let P be a projection valued measure as on the last slide, and then I'm going to use this little L infinity notation for spaces of bounded measurable functions. So little L infinity of omega f is going to be the bounded f Borel measurable functions from omega to c, and I'll put the uniform norm on it, i.e. the sup norm, little L infinity of omega. So the fact is that if you have a bounded measurable function, then there is a unique operator on H such that when you apply that operator to little h and then inner product with k, that's the same as integrating the scalar function phi with respect to the complex measure from the last slide. Moreover, the map that takes phi to the integral, this formal integral at this point, of phi with respect to p is a star homomorphism that satisfies this operator norm bound. So the operator norm of this operator is less than or equal to the uniform norm of phi. And as the notation suggests, I'm going to call this integral the integral of phi with respect to p. So that's a little review of projection valued measures and integrals. All right, so now we'll state the goal of multiple operator integrals. Loosely speaking, if you have k plus 1 projection valued measures on different measurable spaces, but on all the same Hilbert spaces, a multiple operator integral is an object that makes sense of this formal multiple integral, multiple operator integral, for certain functions phi of k plus 1 variables and certain input operators b1 through bk. Now, the first attempt at defining such an object was by Daletsky and Crane in that seminal paper that I mentioned before, and they considered the case where all the omegas are a closed bounded interval containing the spectrum of a bounded self-adjoint operator on H, and all of the projection valued measures are the projection valued spectral measure of A. Now, what they did is they used a Riemann-Stieltjes type approach to make sense of this integral as an iterated integral. So they used the Riemann-Stieltjes type approach to define what it means to integrate an operator valued function against a projection valued measure. So this approach is nice because it actually lets you interpret this as an iterated integral. But the major downside is that it required very strong regularity hypotheses on the function phi, and so it led to very non-optimal results. But that was the first attempt. So the modern approach that I'll show you is due to Peller, and it takes this idea of separating the variables and doing them one at a time to the extreme, more or less. So in 2006, Peller introduced a class of functions that I will now describe, and those are the functions we will be multiple operator integrating. So I'm going to suppose that phi is expressible as an integral of functions of one variable one at a time. So I'm going to assume that there's a sigma finite measure space, sigma, and k plus 1 measurable functions on the product, so that the integral of all of their uniform norms is finite, and that phi is equal to this integral for all k plus 1 tuples omega equals omega 1 through omega k plus 1. So if phi satisfies this, so if there is such a decomposition, I'm going to say that phi belongs to the integral projective tensor product of these L infinity spaces. And this notation is meant to be reminiscent of the classical projective tensor product of Banach spaces. And in fact, if you only take counting measures and countable spaces for this integral, you get the Banach space projective tensor product. If you don't know what those things are, it doesn't matter. We're just talking about functions that admit such a decomposition. And then the norm on this space is going to be the infimum of all of these numbers, where we range over all of these decompositions. And I'm going to insert a little warning. There are some measurability issues. They can be taken care of, but I won't discuss them very much. All right, so those are the functions we're going to be integrating. And then here is the way you define a multiple operator integral of such a function. So suppose we have a decomposition of phi, as in the last slide. Then I'm going to define the formal multiple operator integral of phi with respect to p1 through pk plus 1, evaluated at b1 through bk. So that's this formal integral expression as the following appropriately weak vector valued integral. So I'm going to pause for a second to absorb this formula. Then I will explain a little bit what's going on. Okay, so I've been pushing this interpretation that for a multiple operator integral, what you're supposed to do is kind of split up the variables and do one at a time around the inputs. So what are we doing? We're going inside the integral, and we are integrating out the first variable in P1, sticking in the first input, ... integrating out the kth variable with respect to pk, sticking in the kth input. Then finally integrating out the k plus first variable with respect to pk plus 1. So this is all well and good, but aside from making sense of this integral, it seems that this approach depends heavily on the chosen decomposition. In fact, theorem, it does not. So the MOI from the previous slide does not depend on the chosen decomposition of phi. Also, this operator integral satisfies the operator norm estimate in terms of that integral projective tensor norm of phi for all the input operators. Okay, so a little comment. The initial theorems about well definition, meaning these two, were only proven under the assumption that H is separable. And my contribution here is that I was able to find an argument that worked for not necessarily separable Hilbert spaces, which is nice because this allows for an extension of lots of MOI results to the non-separable case. And extremely, extremely roughly, for those who know what some of these words mean, what you need to do is you need to prove that as a function of B1 through BK, this multiple operator integral is ultra weakly continuous in each of the input B's. And this reduces your calculation to a calculation involving only finite rank operators B1 through BK. And then it is a tractable calculation, and you can give an explicit formula that does not depend on the decomposition. So that's an extremely rough sketch. It's very technical to prove this ultra weak continuity, but there you have it. All right, so now I have described to you how you should actually interpret these multiple operator integrals. And now going forward, I'll tell you what kinds of scalar functions F I'll be considering to differentiate the associated operator function. They're called non-commutative CK functions. And our starting point is going to be polynomials. So I will start with a discussion of the derivatives of polynomials. So I'm going to start out with a normed algebra B. That is a complex algebra with a submultiplicative and unital norm. And now I'm going to let pi m be the power map from B to B. That is the map that takes B to B to the n. A standard exercise shows that pi m is a smooth map from B to B, and it has the following derivative formulas, which are the non-commutative analog of the usual power rule. So the kth directional derivative in the directions B1 through BK of pi m at the point A is equal to, again, you have to symmetrize in the inputs. And then it's this sum, and let's analyze it a little bit. So we are taking k plus 1 length multi-indices whose order, i.e. the sum of the entries, is m minus k. And we're splitting up this power a to the m minus k and distributing it around all of the directions. So this order corresponds to the fact that when you take the kth derivative of x to the m, you need to take down k powers of the input power. So that's this non-commutative power rule. And just as a simpler example, this is the k equals 1 case of one derivative. All right. So now if we apply this to our situation, what we actually get is that if you do the functional calculus associated to the polynomial Pm, which is just the polynomial lambda to the m, then the functional calculus Pm tilde, which is actually just the power map restricted to the self-adjoints, then that is a smooth map, and it has this derivative formula. All right, so I will now analyze this derivative formula to give you the first example that I'll give you, perhaps the only example that I'll give you explicitly of computing a multiple operator integral. So we're going to see that this formula is the desired multiple operator integral that I was describing before. All right, so I'll start with a nice little observation. If I have lambda and mu, then this polynomial of two variables in lambda and mu by some sort of classic geometric series type identities is expressible as this difference quotient. In other words, and of course, if lambda equals mu, we get m times lambda to the m minus 1, which happens to be Pm prime of lambda. So this, by definition, is the first divided difference of the polynomial Pm, i.e. the one that takes lambda to the m. So by induction, one can use the definition of the case divided difference to show that the following is the formula for the case divided difference of the mth power polynomial. It is the function of k plus 1 variables, lambda 1 through lambda k plus 1, that is the sum over these multi-indices with order m minus k of lambda 1 to the delta 1, dot, 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 lambda k plus 1 to the delta k plus 1. And now I'll point out that this is a decomposition of this function of k plus 1 variables as an integral over this finite measure space of functions of one variable, each one at a time. So a product of functions of one variable. So that gives us, if we look at the derivative formula from the previous slide, this guy right here, and we recall the definition of the multiple operator integral, this derivative formula actually says precisely that this derivative is the symmetrization of the desired multiple operator integral. So the summary, if you didn't follow all that, the summary is that at least for the power map, Pm, we have the desired derivative formula for the functional calculus associated with the power polynomial. And if you buy that both sides are linear, then actually this gives the formula that we wanted for all polynomials. Okay, so this gives us some motivation to start with polynomials. And in fact, the space of functions I'll consider will be a closure of polynomials in a certain space. So with that, I can give you the definition of NCK. This is somewhat of a gear switch now. So if you have a CK function and a radius, if you will, r greater than 0, I'm going to define the possibly infinite semi-norm, norm C bracket K comma R. And that's going to be the sum of the uniform norm of F on minus R to R, and then these K integral projective tensor norms. So this is the jth divided difference. And then this is the integral projective tensor product of j plus 1 copies of the little L infinity space minus R to R. And for a given j, Fj may not admit a decomposition as an integral, as I described before. And in that case, we'll just call this norm infinity. So that's for an arbitrary CK function. And now I'm going to define C bracket K to be the set of CK functions for which this semi-norm is actually finite for every r greater than 0. And this, by usual arguments, has a locally convex topology induced by the semi-norms above. And I'm going to define the non-commutative CK functions, NCK of R, to be the closure of polynomials in this space, in this locally convex space, C bracket K. Now, it turns out that NCK is an algebra, and it's closed under complex conjugation, so it's a star algebra. And also, it turns out that it is complete, so it's a Frechet space, if you know that terminology. Just a shout out, this name, non-commutative CK, is taken from David Jekyll, who independently studied a class of functions that is similar. it is defined instead of in terms of these integral projective tensor powers of little L infinity, it's defined in terms of Banach space projective tensor powers of the space of continuous functions on minus R to R. And he studied these in his dissertation. All right, so that is the definition of non-commutative CK. In just a little bit, I will give you large classes of examples of non-commutative CK functions. But for now, I'll jump straight into the derivative formula. Maybe I'll leave this slide up for just a little bit longer to absorb, see if anyone has any questions, but then I'll move on to the derivative formula. Great. All right, so here's the theorem, and I'll start with a little bit of setup. So in general, if you start with some A1 through AK plus 1 and B1 through BK that belong to our C-star algebra that we started with, in general, if phi is in this integral projective tensor product, i.e. we can make sense of multiple operator integrals with it, you can show that this multiple operator integral in general lies in the W star or von Neumann algebra generated by these elements. And that is contained in the von Neumann algebra generated by A, which is in general larger than A if A is a C-star algebra. However, you can show that if F is a non-commutative CK function, then actually this multiple operator integral involving the case divided difference actually belongs to the C-star algebra generated by A1 through AK plus 1 and B1 through BK, and that is contained in A. So this does make sense as an element of A. And actually, the reason this is true is you can do an easy calculation to show it's true for polynomials, and then you can do a norm limiting argument for a non-commutative CK function using the definition of non-commutative CK as certain limits of polynomial. All right, so now I'll make the statement of the theorem. So if F is a non-commutative CK function, then F tilde, the operator function, is CK from the self-adjoint elements of A to A. And we have the derivative formula that I've been motivating. The case directional derivative in the directions B1 through BK at A is the symmetrization of the multiple operator integral of the case divided difference, where I plug in the K plus 1 tuples of all A's, and then I plug in the symmetrized inputs. All right, so once again, I'll give a little bit of a pause to see if anyone has questions. All right. So I'm going to give a little short sketch of the proof, and then I'll discuss some pros and cons of this approach. Briefly, first, the formula is true, as I kind of showed for polynomials before. Next, I'm going to choose a sequence of polynomials converging to our non-commutative CK function in F in the space C bracket K. And then one uses the multiple operator integral operator norm estimates that I showed you earlier to argue that the functional calculus Qn tilde maps converge in CK to F tilde. And what that actually means is that they converge on uniformly unbounded subsets to F, and then also the derivative formulas for Qn tilde converge uniformly unbounded sets to the putative derivative formulas of F tilde, and that is enough to prove the statement. So there are three clear pros for this approach. Number one, no perturbation formulas were necessary, which is nice. And then second, one can make statements about C-star algebras. And then third, it provides a very straightforward natural development that, as I'll discuss very shortly, actually recovers all comparable existing statements for this setting. And the cons kind of go hand in hand with the pros. So number one, this approach is tailored more or less precisely for bounded operators, and no unbounded operators are allowed. You can't quite analyze the unbounded operator case in this setting. And then second, in order to show F belongs to NCK, sometimes you have to do a reasonable amount of scalar analysis on F to show that, meaning that previous criteria were just in terms of more familiar function spaces. And you have to prove that those familiar function spaces actually belong to NCK in order to show that you've generalized previous results. That's not too big of a con, as I'll show you, because NCK is actually quite large. All right, so I'm going to jump into some examples now of non-commutative CK functions. And I'll introduce two maybe less familiar function spaces. And then I'll give you the theorem on examples of non-commutative CK functions. So first, I'll define the kth Wiener space. So this is the space of functions R to C that are roughly the Fourier transform of a complex measure with kth finite moment. Okay, so F is this integral e to the minus I lambda xc integrated with respect to mu. And kth finite moment means the integral of absolute value of xc to the k with respect to the total variation measure, absolute value of mu, that's finite. One can show pretty easily that such a function is ck with bounded 0th through kth derivatives. And then second, I will define Bessoff spaces for you. This takes a little bit of harmonic analysis to appreciate, so you can ignore if you're not familiar. I'm going to fix a bump function, C, so that's a smooth function between 0 and 1 that is identically equal to 1 on the interval from -1 to 1, and that is supported in the interval from -2 to 2. Then I'm going to define this shifted bump function Cj, and here's the formula, but the idea is that this is a bump function that's supported in frequencies of approximately absolute value equal to 2 to the minus j for every integer. And the idea is that if you sum up these shifted bump functions over the integers, you will get the identically 1 function, but 0 at the origin. So that's the idea. Now for a smoothness parameter S, an integrability parameter P, and a Littlewood-Paley summation parameter Q, we're going to define the homogeneous Bessoff space B dot SPQ of R to be the set of tempered distributions F on R such that the following semi-norm is finite. This is the little LQ norm of the sequence 2 to the JS, and then the LP norm of the Fourier multiplier operator Cj of D applied to F. So that's what the Bessoff spaces are. For certain choices of SP and Q, you actually can show that these guys are actually functions and not distributions, but in general, for general parameters, you will get distributions, not functions. All right, so those are the definitions of the Wiener space and Bessoff spaces that I'll use. And here's the theorem on examples of non-commutative CK functions. Theorem, if you fix a K, then first of all, if you are in the kth Wiener space, you are non-commutative CK. Second, if you are in the homogeneous Bessoff space with smoothness parameter K, integrability parameter infinity, and summability parameter 1, then you are non-commutative CK. Third, if you are a CK function whose kth derivative is locally epsilon Holder continuous, then you are NCK. In particular, if you are CK plus 1, then you are in NCK. And then finally, you can actually show that NCK is a strict subset of CK. And just a short word about how you move through the proof of this theorem. You prove through fairly direct means that WK is NCK. And then you can deduce from this that CK plus 1 is NCK. And this fact, together with some non-trivial harmonic analysis that Peller did in that 2006 paper I mentioned, you can prove that this homogeneous Bessoff space is in NCK. And then finally, one deduces from this and generalities about Bessoff spaces that these Holder functions are NCK. The take home from this theorem is in 3 different ways, at least, that if you are just barely a tiny bit better than CK, then you're non-commutative CK. This counterexample here is actually fairly explicit, and I'll just mention that it takes it uses an explicit construction of Potapov, Skripka, Sukhotchev, and Tomskova from 2017. All right, so once again, take home, if you're barely a little bit better than CK, then your operator functions are differentiable. And here's a comment about how this relates to essentially the best known result for derivatives of operator functions. Here is this result that Peller was after in his 2006 paper. If you let H be a separable Hilbert space and A be a not necessarily bounded self-adjoint operator, then if you have f as a sum of a degree 1 polynomial and an inhomogeneous Bessoff space function, which really just means you've got a homogeneous function that is bounded, then Peller proved that this operator function is k times differentiable in the direction of b at a. So that's the kth derivative of this curve. And then the formula is given by the appropriate multiple operator integral formula. So the takeaway here is that I recover, in the case where a is bounded, recover and slightly improve Peller's result from 2006. All right, that is about all I had to share with you today. I'd be happy to take your questions now.